Welcome back at C-Square. In this clip, we're going to talk about the derivative, but I'm going to start with this tangent line because tangent line and the derivative are related. And the first thing you see here on this picture is a circle and a line that is tangent to this point T. And probably you can find the slope of this tangent line using the knowledge in your learning your previous classes. Let's take a look. Here you have a function and you notice is a line that is tangent to this graph, and probably some of you may say, hey, the slope of this line is 0 because it's a horizontal line, which is correct, so it can be found. However, when you have example like the last one on the right, you have to do some other math to find the slope of the tangent line or the equation of the tangent line. And the way we're gonna do it on the first part here is by looking to a numerical way. What do I mean by that? You see that point T that belongs to the graph of f of x. That point T has these two coordinates, c and f of c. How do I find the slope of the tangent line? I cannot go right away there, but I can find the slope of a secant line. You notice this line here, given by these 2 points, it's secant to the curve. I have another point with x and y coordinates, so I can find the run, I can find the rise, and the slope is, if you remember, rise over run. But the beauty of this method, you can go even closer to the point you want to find the slope of the tangent line, and you can calculate the rise again and the run again, and get the slope of that secant line even closer. And look at here in this picture, I have in fact the tangent line, and I want to find the slope of that tangent line. So how this numerical process works, we're going to see in this example. In this example, we have a function given. We need to find the slope of the tangent line at the point 1 and 1. So I'm going to go, you remember in the previous picture, close to 1. So I'm going to start to 1.5. The first thing I'm going to do, I'm going to evaluate the function at 1.5, which means you replace x with 1.5 and you're going to get negative 0.125. And you remember what I said about the slope, that is rise over run. In this case, going to be f of 1.5 minus f of 1 over 1.5 minus 1. So that will be negative 0.125 minus 1 over 1.5 minus 1. And if you do this math, you end up with negative 2.25. The slope of the secant line that goes through these 2 points, 1 and 1 and 1.5 and negative 0.125, it's negative 2.25. I'm going to call this M1 because I'm going to go and find the slope of the line that goes through 1 and 1 and 1.1 and the value of the function of 1.1. So you notice I go closer to my given point, which just has the x coordinate of just 1. The value of the function at 1.1 is 0.791. I'm going to use the same method and I'm going to end up with 0.791 minus 1 over 1.1 minus 1. And if I evaluate this expression, I get negative 2.09. Well, now I can go even closer to 1.01. I'm going to evaluate the function of at 1.01 and I end up with 0.979, and then I'm going to use again the slope formula and I'm going to get 0.979 minus 1 over 1.01 minus 1. If you evaluate this quotient, you're going to end up with negative 2.009. And of course, some of you may want to go even closer. I'm not going to go, but I think if you do this math, you're going to notice the slope, I'm going to call it M4 here, is going to be probably this one. So you notice Once x gets closer and closer to 1, the slope goes closer and closer to -2. That is the slope of the tangent line, which you're going to see it right here. And if you take a look to the graph, yes, the slope is 2. And this is a numerical way to find the slope of the tangent line. This is the limit process, which is going to help you to find the slope of the tangent line, because obviously you see, if you go closer and closer to this tangent point, you should think about limits, and this limit will help you to do the slope of the tangent line faster instead of using the numerical way. I'm going to show you that in this example. So the slope of the tangent line is limit when delta x approach to 0. Yes, that run getting closer to 0 of f of, and now in our case the c is 1 plus delta x minus f of 1 over delta x. And the first thing I'm going to do here, I'm going to evaluate f of 1 plus delta x for this function f of x. So I'm going to have 1 plus delta x squared plus 2, and that will be 1 squared, in fact, which is 1, plus 2 delta x plus delta x squared. If you need to fold that expression, do it, plus 2. So if we simplify this, we're going to have 3 plus 2 delta x plus delta x squared. And now let's evaluate also f of 1, which means you're going to replace x of 1, 1 squared plus 2, and that is 3. So now we can go back here, and we're going to have limit when delta x approach to 0 of 3 plus 2 delta x plus delta x square minus 3 over delta x. And my next thing will be to simplify these two. These negative 3 and 3 cancel out. And yes, delta x also cancel out. If you take a look, I'm going to move down here, and I'm going to have limit when delta x approach to 0, and the numerator, I can factor out the delta x, and then I have 2 plus delta x over delta x, and now the delta x cancel out, and my limit becomes just limit when delta x approach to 0 of 2 plus delta x, and when delta x approach to 0, we end up with 2. The slope of the tangent line is 2, and you can see that in the picture also. The slope of that tangent line at 1 and 1 is 2. And as you notice here, this is the definition of a derivative, and this definition is so similar with the slope of the tangent line. The only difference, we have x instead of c. Other than that, is the same. That's the reason I said the tangent line and the derivative are related at the beginning of the clip. And in this example, I'm going to show you how to find the derivative when using this definition. So the derivative of this function will be limit when delta x approach to 0 of f of x plus delta x minus f of x over delta x. So we have here to do f of x plus delta x, evaluate this expression, and that will be x plus delta x square minus 3 times x plus delta x. So in this case we have x squared plus 2x delta x plus delta x squared. This is the first part, And then here distributive property minus 3x minus 3 delta x. So we can go back in this limit, and we have limit when delta x approach to 0, and let's replace f of x plus delta x with x squared plus 2x delta x plus delta x squared minus 3x minus 3 delta x minus f of x minus x squared, and be careful here, plus 3x over delta x. And let's see what's happening here. The first thing you should notice, the x squared cancel out, and also negative 3x and positive 3x. So what we have now is limit when delta x approach to 0 of, and here we can factor out the delta x for the numerator, and we have 2x plus delta x minus 3 over delta x. And again we notice these cancel out, so the limit becomes limit when delta x approach to 0 of 2x plus delta x minus 3. Then when delta x approach to 0, we end up with 2x minus 3. This is the derivative of the function using the limit process. Later we're going to learn another way to do this derivative. In this moment, the limit process gives us the derivative of function f of x equals x squared minus 3x is 2x minus 3. The last part of the clip, this is an alternate form of the definition of the derivative. It's a local definition. Will help you to, in case you want to see if a function is differentiable at a point, because you can write similar limits to the left and to the right of C. Also, very important theorem that if f of x is differentiable at x equals c, then f of x is continuous at x equals c. The converse doesn't work. Be careful all the time, but this one works all the time. And the last thing, these are some notation you may see, and they means derivative. I just use this one. This is called dy over dx, y prime, or this one is f prime, and sometimes you may see even this one. If you enjoyed this video clip, don't forget to click the like button and come back on C Square for more help. Thank you.